Welcome back, everyone. Today I want to talk a little bit about interrupts and how the Z80 handles the interrupts. It's got three modes of interrupts. The mode 0 basically emulated the Intel 8080, and mode 1 called a static address. I think it was hex 38. And then mode 3 is the most comprehensive, and it actually is able to work with the PIO and the SIO and the CTC chips, but it basically allows the device that's interrupting to put an address on the line, and it'll get called. So we'll go in detail, but right now, when we start talking about interrupts, we need something to interrupt. So first thing I'm going to do is I'm going to build a switch that's debounced, and basically get that ready, and then I'm going to hook it up to the Pony80, and we can start writing some code to handle all of these interrupts. So let me get this going, and then we'll go from there. So what I've got here is a Schmidt trigger inverter and an HCT14 is what that is. And I'm going to run a signal into it coming out of a capacitor resistor network. And let me get this set up here. So basically what's happening here is, if you saw the video about my timer, or not the timer, sorry, the clock, for the Pony80, this is kind of the same theory, that as I push this button, it's going to charge this capacitor, and then when it hits a certain threshold, it's going to turn on pin 2 of this inverter. Sorry, it's going to turn it off, and then when I let go, it's going to turn it back on. Again, all draining through either the button when it's pushed or this resistor. This resistor right here. Now we want to test this to make sure I've got it set up well. So what I'm going to do, or set up right, what I'm going to do is I'm going to use my Arduino. You saw this in the troubleshooting video. If you've seen that video. If you haven't, go check it out right there. But I've got this pin hooked up to, this wire hooked up to pin 2, which is one of the digital pins. And that's what I'm going to use to measure the output, because I can set an interrupt on that and basically watch how many times that interrupt occurs as I'm pushing the button. We should only get it to interrupt once each push. So hook up the ground there. All right, now I'm going to plug the Arduino into my laptop, and we'll go from there. I guess it would also help if I put some power on the, no, let's put it the right way. Put some power on the breadboard. So I've got my 5-volt adapter. All right, let's go write a quick program to monitor this. All right, so here we are in the sketch. Let me go ahead and get this started. Let's see. Just do some housekeeping here. We'll include the library so we can print stuff out. Now, the only pin I'm going to need is the pin 2 that I put the wire in. So I'm just going to call it pin. That's really. And then I'm going to instantiate a variable that will hold our count. And then let's get this set up. And on that pin, I want the pin mode to be input, so we'll set that. And then what I want to do is I want to set up an interrupt so that all I have to do is press the button and the Arduino will count it. So there we go. And we'll call it on press, and we'll do it on the rising of the clock, or it's not the clock, it's the button push. Nope, it's not capitalized. Get our serial all set up. There we go. And now we'll create on press. And all this is really going to do is count, or increment the count, and then output it. But speaking of which, first thing is I will need a variable to put the string in that's going to be sent out to the serial. And then we're going to increment the count, and then we're going to format the string. And let's do just a number. Not going to do any kind of labels. There we go. And then oh, you know what I totally missed on the sprintf? It's hard to dictate what you're doing and do it at the same time. There we go. All right. So let's go ahead and build this and upload it. What did it? Oh. Not needed, but yet needed. All right. Now let's go to our serial monitor here. But if I go ahead and turn this on, okay, you got a couple of clicks just because the power came on, but let's push it. All right, looks like we've got our single pulse generated, so we can then generate that interrupt and test that. Now let's get the Pony80 out, and let's hook up to the interrupt pin on the backplane, and then we will write some code and test that. So as you can see here, if we look at the Z80 user manual, there are two types of interrupts on the Z80. One of them is the regular interrupt that is maskable in software. You can turn it on, turn it off. And if you turn it off, nothing happens when the interrupt is raised. But there's also the non-maskable interrupt. And if that pin goes low, it's going to interrupt. It's going to it's going to respond to that interrupt. So if we look down here, and no, that's the wrong way. Let's go this way. There we are. There we go. Let me see. I'm looking for. Here we go. Right here. So the CPU will always accept a non-maskable interrupt. And when it's accepted, meaning when the pin goes low, the CPU will accept it. Actually, it'll finish the command. The command that it's working on right now. It'll finish that cycle. And then it'll accept the non-maskable interrupt. And it basically does a restart at address 66 hex. And so it puts the current stack pointer, I'm sorry, not stack pointer, the current program counter on the stack, and then it jumps to 66. And then it'll execute whatever at 66 hex until it hits an RETN, return from non-maskable interrupt. And then it pulls that address off of the stack and puts it in the program counter and continues where it was. So I think the first thing we're going to try to do is just see what we can do with the non-maskable interrupt. And if we push our button and we get it to respond, then we know we've got that right. So let's move over to the breadboard and the Pony80. And so here's my breadboard. Now, I don't know if you caught what I was saying, but the non-maskable interrupt and the interrupt themselves actually respond when the pin is pulled low. So that means that, let me see if I can get this right here. Yeah, here we go. So on the Pony80 card, we've got several pull-up resistors for things like the non-maskable interrupt and the interrupt. So they're not floating, because a floating pin is never a good thing. They're pulled high, and then when the pin for the NMI and the int get pulled low, then it signals the CPU to go ahead and respond to that. But if you remember from our Arduino example, when I push the button, it would go high. So what I'm going to do is I'm actually going to take the output of pin 2 on this inverter, put it to pin 3, which will invert that rising, and then make it a falling. And that falling is what we can put then onto the backplane and use it to trigger the NMI, non-maskable interrupt. So let me get that set up and get the Pony80 over here. If you remember, if you've seen the, it seems like I keep pushing this, but it actually is relevant. If you've seen the troubleshooting video, it is because I don't have any resistors, and it is because we've got reflection on the bus. And so what I need to do is I need to add some resistors to the 8 data bits, and add a 10K resistor array to the 8 data bits, so we can stop that whole thing from happening. All right, so here's the resistor array that I have, and it's a 10K resistor array. This pin right here is the ground, and the other 8 go to resistors. So let me plug this in here. And so we have the 8 data wires going into this this resistor array, and I will then tie the ground. There we go. And that'll keep our and just for fun, let's go ahead and look at our output and turn on the we might be missing something. Let me plug this back in here. I mean, it's just the CPU. What is it Jason Lee says in Almost Famous? Oh, sure, it's easy to forget me. I'm just the lead singer. And if you haven't seen Almost Famous, go see it. Or don't go see it, but just rent it. Ah, it doesn't work, but I know why. Again, a floating pin is never a good thing. So I have this hooked up to 5 volts and this hooked up to ground. I'll go ahead and hook that up to our breadboard so that this ground here actually goes somewhere. Let's take a look. And there we go. And I'll explain later, or maybe I'll just explain on my Patreon account what all these numbers are, because it was actually a fun little experiment that I was doing fairly late at night, which is when all my good ideas happen. All right, I'm going to move these down here so that they're not really in the way of what we're doing. Try to get them out of the way. All right, so we know the Pony80 is working, and we've got the push button here, but we do need to make sure that we invert this signal. So I've got a jumper right here. I don't know if you can see that tiny little jumper. And we're going to go from pin 2 to pin 3. And then go ahead and pull this out. If you'll notice, I've got this red wire hooked up to the non-maskable interrupt. This breakout board is just super ideal. It allows me to be the mad scientist that I always thought I was. All right, so we've hooked that up to the non-maskable interrupt. But the problem is, our software is not going to handle it right now. So let's jump over to the IDE, and let's do a real quick quote-unquote operating system just to handle the non-maskable interrupt and be able to display something on the display when we click on it. Okay, so here we are in Visual Studio Code, and you notice I've got just an abbreviated bit of code here, really just enough to test this NMI. And so I'm setting the address for the LCD command and data and the ROM page, even though I'm not using that right now. Then I set the stack pointer to the top of the stack. And then right here you see I've got this command called EXX. And what EXX does is it swaps out the second register pair for the second set of registers for the first set of registers. So if you're not familiar, in the Z80 there is actually a shadow set of registers. It has two full sets of registers. And by executing this command, you can very quickly get to that other set. And it takes, I think, one instruction cycle. Let's pull it up here in the user's guide. So yeah, it takes one instruction cycle, but basically just swaps them out. And in interrupts, it's actually quite important that the interrupt finishes as quickly as possible. So you notice that like I said, this EXX happens in one instruction cycle. So when you get down here into the interrupt, which I'll get to in a minute, it really makes this go faster. So I'm swapping out the sets of registers. I'm loading HL with 0, and then I'm swapping them back out. Now what I'm doing here is, rather than writing a counter to memory or trying to keep it in one of the registers and not have it overwritten or anything like that, I just swapped it out. Now this is a very simplistic example, because there are other ways to do it and it would be fine. I could load HL and just not touch it because I've only got this much code right here. However, then I'd have to push HL here and then pop it after that. And again, all that takes cycles. So I was just trying to get as quick as possible. So swap out the registers, clear out HL and make it 0, and then swap them back so it's originally. And then we initialize the LCD, and then we load HL with the power up message, and then call the LCD display message. And the power up message is right down here. And that will be displayed on the screen. And I just realized that I forgot a delay. And all this delay does is, that's not what I want to do, is counts 255 the number of times loaded into A. And I'll show you here the code in just a minute. But that way the message can stay on the screen, and then we jump to main, which will clear the LCD. That's redundant. I don't need to do that, but there we go. Now I'm going to load HL with the NMI label, which is down here, and it just says NMI : space. And then I'm going to swap out the registers again, and I'm just going to display HL. So each of these calls is one instruction cycle each. I'm sorry, not up here. Each of these calls is one instruction cycle. I meant to mention that when I was back up there, so I apologize. I'm not trying to confuse anybody. But EXX is one cycle, increment HL is one cycle, and EXX is one cycle. So again, very fast at processing interrupts, 3 cycles. So down here, like I said, clear the LCD, swap out the registers, display what's in HL, swap them back, and then delay for a little bit, just so that if I'm running at higher speeds, the display shows up. And then jump back to main. And so main is just looping here, and all it's doing is it's loading HL and printing it out. But the real magic happens right here. This org $66, that is if you remember from looking at the data sheet, that is the address that the NMI interrupt always goes to. Doesn't matter what causes it, it's always going to go right here. So it'll jump back to this 66. It'll swap the registers, increment HL, and swap the registers again. And again, all 3 of these happen in one instruction cycle, and so it's extremely quick. And then it returns from the NMI. So this only happens when I push the button, or when NMI goes low. And then all this just continually loops. I'll show you the delay function. So the delay, we're going to load B 255, and then we're going to decrement and jump non-zero, which means it's going to go right back here. So it's going to decrement and jump until it equals 0. Then it's going to come down here and decrement A. And if A is 0, it's going to go down here to return and pop the stack and return back to the caller. If A is not 0, it's going to go back up here to this one, load B with 255 again, count down until it's 0, decrement A, look for 0, and that's all it does. And it's very inefficient, but it takes control of the system. And the other issue with it is that if I use different speed CPUs, I've got to adjust how much I load into the accumulator, because a 10 megahertz processor will probably need, a processor running at 10 megahertz will probably need 2 or 3 delays in a row to notice anything, whereas a 1 megahertz I can get by with just a little bit of delay. I actually have a fix for that coming up. It's in a couple of videos, 3 videos, I don't know. It's down the line. It's one of the next components. I'm putting a keyboard interface, and then I'm going to do a fixed speed timer so we can get the number of ticks 1,000 a second. So we'll get to that. That's just a little teaser. So all that's done. Let me save this, and then I will compile it. And let me get my memory chip out of the Pony80, the EEPROM. Throw it into my programmer. And then load her up in programmer. Now, if you look, where is it here? Oh, I'm in the LCD module. Here we go. If you look right here, this is the interrupt starting at 66 and has 3 bytes, and that's it. D9, 23, and a D9. So swap the registers, increment HL, and then swap the registers again. So that makes it super, super quick. So, all right, so let's test it and get it set up on our breadboard here. All right, so let's test it. If I push the button here, once the NMI prompt comes up, I should get a 1, then a 2, then a 3. Let's see. 1, 2, 3, 4, 5. So that's how the NMI interrupt works. Basically, it's non-maskable, so you can't turn it off in software, and it's usable for whatever. The only caution is it's reentrant. So if you're in the middle of an NMI interrupt and another NMI interrupt happens from the same device or a different device, it's going to restart at 66, hex 66. So that could be an issue. For our issue, for our usage, we probably won't use it for anything other than maybe a power outage situation to copy memory to SD before it, goes out. We'll talk about that in a later video, but not really a big use of the NMI. So for me. All right, so the mode 0 interrupts basically copied the 8080 microprocessor interrupt. And it's no surprise since the same team worked on the 8080 that worked on the Z80. So what happened is you got to put a byte on the data bus, and it would run that instruction after you called the interrupt. So let's go to the instruction that you could call was the 1 byte reset instruction right here. And basically it's a 11, AAA 111, and the AAA was what address you wanted it to interrupt to. So if you put all zeros, it would jump to interrupt 0. If you put all ones, it would jump to 38 hex and all in between. And that allowed device manufacturers to put, jumpers to configure these 3 pins, and the user could, make one card interrupted 08 and another card interrupted 020, and it would basically then, if you had the drivers installed, it would jump to another address that would run what needed to happen. So, yeah, that's how that works. I'm not really going to demo it just because it's pretty cut and dry, but I'm also never going to use it. This is something that was put in for backwards compatibility. When they developed the Z80, they really wanted to have that 8080 compatibility. So, because that was the state-of-the-art microprocessor at the time. So, but that's how that works. And we'll move on to mode 1, which is a little like the NMI. It, if I go back to where we were here, oops, one more. There we go. There we are. Mode 1, it's exactly like the NMI, except it goes to location 38 hex in the 0 page instead of 66. So when the interrupt pin went low, it would just execute whatever at 38. Again, not very useful for what we're going to do. I could see, the use in this for non-Zilog chips, like the PIO, the SIO, the CTC. But the real meat here is going to be mode 2. And this is a really amazing interrupt system for the time. Basically, you get to say, and you load into the I register, okay, my address map is located in this bank of memory. So, for example, you put it in 00. That's the high bytes of the interrupt address. And then the device that's causing the interrupt puts the other 8 bytes on the data bus. And so between the two, you get a 16-bit address, which is 64K bytes. So you could go anywhere in memory. It is very, very powerful. I'm going to talk a lot about this when I'm in the next video for the keyboard module.
because I use a PIO and I use mode 2 interrupts. So basically, here's how it works. The register I contents form the high bytes, and then the 7 bits from the peripheral finish that address with a 0 at the end, because each of the bytes have to be even, so that because you have 2 bytes to make up the 64K address. So you have the I register 8 bits, the 7 bits that come from the peripheral, and then a 0. And that's literally what gets executed next into the program counter, or gets loaded in the program counter and executed next. So really cool. It is there's a lot more detail, like we've got 2 pins on the PIO and the SIO called IEI and IEO, which is interrupt enable input and interrupt enable output, which allows you to configure which priority you want each card or each device to perform. If you tie the interrupt enable input to high, that's going to be priority 0, which means when it calls an interrupt, it's going to execute immediately, no matter what other interrupts are happening. But you can then daisy chain them and put the output from one card into the input of another, and that will say, hey, you're higher priority than I am, so here's where I am. But if somebody higher than me is connected to the input, I may not be able to do an interrupt because you're already doing an interrupt. And like I said, we'll get into you'll understand this. You'll see it in action. Let's put it that way when I do the next video. So that's basically an overview of all the interrupts of the Z80. It is very robust, and for that reason, it was used a lot in embedded systems and command and control type systems. So it's I think that accounts for a lot of the widespreadness of the Z80 and the fact that the Z80 is still purchasable today. I'm able to buy 6 megahertz Z80 chips from Mouser and use them in this video, and it's for me, it's really interesting because it's 1970s technology, but it's of course been updated to CMOS, and the clock speeds have gone up to 20 megahertz, I believe is the top now for the Z80 itself. But this interrupt system makes it very easy to implement a full system to control external electronics, because you've got stuff like the PIO and the SIO, and PIO is the parallel interface something, and serial interface is the SIO. And I apologize, I don't remember what the O stands for, but yeah, it's definitely a really convenient and lower chip count system because of the way they've implemented these interrupts. So anyways, that's it for interrupts. Next, I'll be talking about the keyboard interface. I'm going to do a short video here in between somewhere about the resistors that I've put on the data bus to kind of stop the weirdness from happening. But it won't be a short, but it'll definitely be one of the basics. I did a huge deep dive into bus resistors, whether it's terminating, whether it's pulling them low, and I've got a lot of good information that I want to share, so I'm going to put together a dedicated video on that. So anyways, leave me any feedback that you have. I love reading the comments. I try to answer all of them. I've gotten a lot of good information from them. I've also gotten comments that definitely support where I'm going with this. And I don't want to come off as flippant or casual when somebody gives me a comment and a suggestion or some advice, and I go, "Oh yeah, that's where I'm going." But at the same time, I'm going through this and I'm learning it the same way, and so, I have been doing a lot of research on stuff, so it's really great to hear people just confirm the research that I've done, and I appreciate it. And I look forward to talking to more of you. It really does make my day when I get a comment. So thank you, and have a great rest of your day. Talk to you later.